And hello, welcome to this next video of Laplace Transforms. Last time we were talking about Laplace transform of some exponentials, okay, e to the minus at, where a is some positive number, positive real number. Okay, so let's deal with the other side. I think it's going to be pretty much the same. So we'll have Laplace transform of e to the minus at this time. You can do that very quickly. So e to the minus at is actually, yeah, you'll just have this. Okay, so basically I can just copy and paste the top and I'll just replace all the all the places where I have a with minus a. Okay, but yeah, so okay, maybe it's better to explain. Okay, so I'll just factorize out this 2. I'll factorize out t. So I'll factorize out t, and then I'll have this. Okay, I'll have this, and of course then we'll need to have our fractions again, and then we'll take the limits. Okay, a plus s, and we'll have minus at. So of course, first glance, you have e to the minus at resulting in s minus a. So how come the signs switch? Okay, so e minus at becomes a plus s. Why do the signs switch? Okay, so let's yeah, why do the signs switch at all? Okay, yeah, so that's a little bit of a problem, isn't it? Okay, the signs are switching. So what's the deal with that? Okay, so the thing is that, yeah, remember this whole mechanism is there to help you to find all the poles or the peaks. So basically, if again s equals to a, if you plot on your s plane, where you find all the complex frequencies, okay, if you plot everything out on your s plane, okay, you have your imaginary and your real, because s equals to some complex frequency, sigma plus j or I omega. Some people like to use j. If you like to use I, that's fine as well. Whichever, just know that it's imaginary. So if you have s minus a, right? If you have s minus a, that means okay, or rather you have a 1 over s minus a. Your pole will be at s equals to a, because you look at the denominator. Okay, you look at the denominator and you equate it to 0. Okay, you look at the denominator and equate it to 0. That's why if you take a, you bring a to the right hand side, you just have s equals to a, and that will tell you where the pole is. So the thing is, if you want to find out where your poles are, just equate your denominator to 0, and then you will be able to find where these characteristic time constants are by just equating the denominator equals to 0. Yeah. Okay, but that's an important thing to know when you want to find poles. Okay, so e to the minus at, where a is a real number. A is a real number. Why do I have a e? Oh, okay. So this should be subparagraph. Okay, let me do this. Negative exponential. Okay, so negative exponentials. Okay, so let me put this here, and let's put at the top positive exponentials. All right, there you go. I think we're all set now. So yeah, for positive exponentials we have a problem, but for negative exponentials, note that a is more than 0 and is real. Okay, let's use the dollar sign here to turn this into more than or equal to sign. Okay, a is more than 0 and is real. Okay, and s is of course complex frequency. So of course s must be okay, whatever your conditions for this thing to work. Okay, you don't want to have a plus s being a negative number. So your condition for this to work is for a plus s more than 0. Okay, if not, you'll have this infinity problem again. Okay, so a plus s more than 0 for all of these things to work. Okay, so so that your first term will just drop out to 0, and what will your next term be? I will just skip out all the pretty much most of the steps. Or okay, maybe I'll just write it down first at least. Okay, so I'll just copy and paste. I'll copy and paste this here. Okay, minus a plus s to the infinity, a plus s. Okay, then you have a plus s. Alright. So as long as a plus s is more than 0, this thing actually holds. So the first term will just drop to 0 very conveniently. Second term, okay, yeah, I think I mixed up something. There should be the denominator should have a minus sign. Okay, the denominator should have a minus sign because you divided it throughout. The minus should appear throughout. So let's just do a minus s. Okay, do post it in the comments if you ever see careless mistakes. All right, it's a great help to people around. Yeah, because I know I made them a lot. Anyway, long and short, the summary is this: Laplace transform of negative exponentials as long as a plus s more than 0 will be this. Okay, 1 over a plus s. Very, very neat, very easy. And if you actually plot it out on your if you actually plot it out on this what do you call that? The s-plane, your poles will be over here. Okay, your poles over here. Doesn't mean that there's a negative doesn't mean that you know, your frequency somehow goes negative, no. But your time constant, right? Your time constant is actually just e to the minus at. Okay, so your constant in front is minus a, so it'll be in the minus side of this s-plane, where you have the amplitude and yeah, you have the amplitude and everything. So this is e to the at, which will be in the positive side of the s-plane. So we like to call this the right hand side, RHS, of the s-plane. And this is the left hand side, LHS, of the s-plane. Okay, so that's basically it. Okay, now we find that these exponentials are pretty simple. Okay, so let's go to the next thing. All right. Let's go to the next thing. Imaginary exponential. Okay, why do we want to concern ourselves with imaginary exponential? They're actually the basic building blocks of sines and cosines. Okay, imaginary exponentials are your basic building blocks of sines and cosines. If you actually look at Euler's formula from Wikipedia, okay, so I'll just refer to Euler's formula in Wikipedia. You actually find that cosine of x, okay, cosine of x, cos of x, or we'll just do it cos of omega t, because we like to deal with sines and cosines in a frequency format. Cos of omega x is equal to fraction exponential what? I omega t, okay, minus or plus exponential minus I omega t over 2. So I mean, yeah, of course we can of course do the sine part as well, which what is ix minus I omega t minus I omega t over 2i. So this will be a sine, not a cosine. Well, I mean, the shape is more or less the same. It's just that there's a 90-degree or pi by 2 phase difference. Okay, so this is why we want to concern ourselves with imaginary exponentials, because these things actually help us to deal with what do you call that? Deal with sines and cosines a lot easier. Okay, once you know exponential I omega t, or I omega t, exponential I omega t, and exponential minus I omega t, you'll be able to compute sines and cosine Laplace transforms without any issue. So again, let's do this again. E to the minus I omega t. Okay, e to the minus I omega t, and that will be your Laplace transform. Okay, so remember, Laplace transform is always to deal with negative exponential, right? I mean, it's a complex frequency, I'm sorry. Alright, so how do we deal with this? Okay, how do we deal with this? Alright, let's see. Okay, so basically the steps are the same, right? Just treat I as, just another number. Okay, just another constant. Okay, we don't really need to worry about I. I is just another constant. I mean, it's a little bit harder to wrap your head around imaginary exponentials, but this is how it works, how we will do it. Okay, same idea. Then we'll just do the standard integration. Okay, standard integration. Okay, so we don't have to go and try to rack our heads thinking about sines and cosines, because now we already deal with exponential integrals, so we can just substitute in an imaginary exponential and see what happens. Okay, so again, same idea. Alright, same idea. So e to the minus I omega t, I will need I omega at the bottom and I omega at the top. I omega at the bottom and I omega at the top. I omega, where omega is whatever frequency or whatever you want. You can put minus b if it confuses you less. Okay, but whichever, okay, whichever, whatever. Again, you will have the same idea. I omega plus s. Okay, that should be a negative number. Okay, hopefully it's negative, right? Okay, I omega plus s should be more than 0. Okay, so this is how you do the negative imaginary exponentials. But of course, this may not make sense, because there's a complex number part, there's a real number part. But okay, assume we just throw that out the window, and yeah, because for the most part with Laplace transforms, we don't really, at least with the standard table of Laplace transforms, we don't really worry too much about this so-called convergence problem. We like to just assume it's all in the region of convergence. But in your derivation, I mean, what is region of convergence? Region of convergence is just a place where you don't have this infinity problem. Okay, that's the long and short of it. So you don't want your Laplace transform to just go to infinity. So we assume this is the condition, and then we'll just put this standard Laplace transform. Okay, not to worry. Nothing too complex, if you get what I mean. Catch my drift. Yeah, nothing too complex here. It's just imaginary exponentials. So this thing will just drop to 0. And then of course the negative sign will actually just disappear. Why? Because if you saw earlier, yeah, the negative signs here actually cancel each other out and they'll just disappear. Okay. Now so we can also do the same thing for this exponential I omega t, same idea. And of course we'll need to put in the what do you call that? Make sure you have the correct conditions. Okay. Same idea. Then basically I can just copy and paste all of this down, and yeah, I'll just copy all of this down and just replace everything with I omega. Everywhere I see A, I'll just put I omega inside. So I just put I omega. Okay, I'll just copy and paste. Wherever I see A, I'll just copy and paste I omega in. So it's basically the same. You just treat it as if, you know, this was a real thing. Okay, now the thing is, you will need to assume again. I do this very loosely, alright? I omega more than S. Okay, assume I omega more than S so that you don't have this convergence issue again. Then your whole thing will just reduce down. Again, very simple. Let's see. Here will be, this will be what do you call that? The first term will be 0. Okay, 0 plus, okay, fraction 1 over S minus I omega. Alright, so very fast. We will just get this. Okay, assuming we don't have all this this problem, the infinity problem. So I just kind of skip and throw that out. So now we can do sines and cosines. Okay, so I do sub maybe sines. Now we can do sines and cosines. So let's do a cosine first. Okay, so cosine first, very easy. Let's see how much time I have remaining first. Okay, alright, so cosines is this. So let's just do a Laplace of that. So I'll just do math cal. Laplace of this. Okay, I want a cosine omega t. Oh, right. Math cal L of cosine omega t. Okay, the 2 we can just leave it out, and then we'll just add these two things together, right? You just add these two things together. What is this? Exponential I omega t, that will be 1 minus I omega. Right, we just derive that. Copy paste. Alright, copy paste. Now of course we can take the fractions out. So we'll have half in front. Fraction 1 half. And this other thing here will just become 1 plus I omega. 1 over 1, or S plus I omega. Okay. Ooh, that doesn't look good. 1 I omega. It's just I omega. Okay, the thing just disappeared. Okay, there you go. Much better. I need a half in front, so half. Okay, so not too bad. Basically, if you combine these two fractions, you do this partial fraction thingy. You just have this. Okay, so you multiply the bottom out. Okay, you multiply the bottom out, it become S squared plus omega squared. Because that's how you multiply complex conjugates. Complex conjugates. So you will have 2 at the bottom. So right over here. So I'll take out the half, factorize out the half. Okay, so on top won't just be 1. I'll have a S plus I omega on the left hand side and S plus minus I omega on the right hand side. So s plus I omega on the first term and s minus I omega on the second term. Alright. So now we can just add them together. The I omegas will cancel out. And s plus s is just 2s. 2s divided by 2 is just s. So I think from here you can just see very easily that this is just s plus s over s squared plus omega squared. Okay, now we have derived our cosines. We can just repeat the same thing for sines very easily. Let's see whether we get our Laplace correctly. Yeah, so you can see on Wikipedia what are some of the tables. This Laplace table. Table of selected Laplace transforms. Haha. Okay, look, sine and cosine are here. The cosines will be here. S over s squared plus omega squared. We just derived it. Ta-da! Okay, not that difficult. If you know your exponentials Laplace transform well, you can do sines and cosines very easily. And let's do sines then. Let's do sines. So I'm just gonna copy and paste all the things about cosines. So let's do sines as well. Sines, not sines, but sines. Okay. So what's the definition? Okay, sine omega t exponential I omega t minus exponential I omega t. So we'll need to do slightly different. Here we have sine, then exponential I omega t minus exponential I omega t, and you divide it by 2i. Okay, don't let the 2i scare you. We'll just factorize that out and we'll worry about that later. Okay, 2i here and 2i here. Okay, and instead of a plus, we'll have a minus. So we'll have the complex conjugates behave a little bit differently. So this plus will become a minus. Now what happens when you have a minus? What happens when you have a minus? And I have to change this to signs. Excuse me. I have to change this to signs. And we'll just have the minus so that the s will cancel out, and then you just have 2i omega on top. 2i omega on top divided by 2i, you will just have omega on top. So you'll have omega. And there you go. Very simple. Again, this is not cosine omega t, this is sine omega t. So want you to know that, once you got your exponentials out, you can already do normal exponential Laplace transforms, sine and cosine Laplace transforms, and well, you can even do complex sine and cosines, you see? Excuse me. So remember, we have this term. Okay, we have s being some complex frequency. Okay, so if you have a pole somewhere not on the real axis or on the imaginary axis, but somewhere in between, then you have some form like this: at sine omega t, sine or cosine, whichever it is, doesn't really matter. You just care about the poles. The poles will actually tell you. Well, they are very telling of what these things are. So if you have something on the complex plane, if you have a pole in the complex part, neither on the real or on the imaginary, you have Laplace. You're actually Laplace transforming something of this sort, where you have an exponential multiplied by a sine. Okay. So I think that's it for now. I'll just take a break. 24 minutes already. I'll take a break. Then we'll talk about complex exponentials if we have time. Yeah. I mean, so yeah. See you next time. Okay.